All right, so a lot of students have problems with these types of problems. So let's go ahead and take a look at some examples and figure out how to do these kinds of problems. So when you're trying to pick the right answer for one of these problems, first thing you want to do between the two molecules, if it's asking, what's more acidic, what's more basic, you want to find why they're different. So find the differences. Are the atoms different? Are the charges different? Yeah, do you have different resonance structures, induction, hybridization, that kind of thing? And then when you find the differences, you want to rank the differences. Remember our order. The most important thing here is charge, followed by atom effects. And then remember, with atom effects, you have to think about whether you're talking about across a period or down a group. Resonance structures, we have to think about resonance structures. And then when we're thinking about resonance structures, not only do we want to think about how many resonance structures do we have, but are any of those resonance structures, do we have a negative charge on a more stable atom? Number 4 thing we want to think about is induction. And then number 5 thing we want to think about is hybridization, or the orbitals. And then the number 3 thing that you want to do is you want to read the question carefully, right? Because it can get very confusing. Sometimes I'll ask which one of these is the stronger acid. Other times I'll ask which one's the stronger base, right? So you want to make sure that you understand what the question is, right? And then obviously the last step is give the right answer. So follow these steps and it shouldn't be too bad. Let's take a look at some examples. So here we have this guy versus HCl, right? And the question here we have is, which one of these is the stronger acid? And so the first thing we want to identify is what's different about this, right? Here we have an OH bond, so we have an oxygen next to the H. Here we have a chlorine next to the H. And so what we're thinking about here is atom effects. And if you think about where these atoms are, oxygen is here, fluorine is here, and then chlorine is down here. And so what we're talking about is going down the periodic table, and if you're kind of going sideways on the periodic table, it's the down that's going to dominate. Size in general is going to be the more important factor, right? And so chlorine is going to be the bigger atom, and so it's going to stabilize that negative charge better. And so this one right here will be the stronger acid. And this makes sense from what you learned in Gen Chem 101 or 102, right? You learned that hydrochloric acid, HCl, is a strong acid. This alcohol is obviously not a strong acid because you drink alcohol, and so if it was a strong acid, you'd be dead. Another question we could ask is, which one of these is the stronger base? Right, so the first thing we want to take a look at is what's the difference between these two compounds. They both have an OH bond and they're both neutral, so it's not charge and it's not atom effects. And so if we were to think about putting a negative charge on this oxygen because we're giving up an H+, it would reside only on this oxygen. Whereas this oxygen here would get a negative charge, but it would then be in resonance with this other oxygen. And so we've delocalized the negative charge. And so the one on the left is going to be more stable in its negative charge, which means it's going to be the stronger acid, because it has more resonance structures. But remember what the question is asking. It's asking which one's the stronger base, not what's the stronger acid. And so the correct answer here is the one on the right. So always make sure you are reading the question carefully and correctly. Another question that's often asked is, which is more acidic? And so we'll take a look at a molecule. I'll label some of these protons, and then I'll ask which proton is more acidic, right? Is HA more acidic or is HB more acidic? And so if you're thinking about getting rid of HA, you'd have a negative charge here that could then be in resonance with this double bonded oxygen. but not with the other oxygen. Whereas if we remove HB and place a negative charge here, it can be in resonance with both of these double bonded oxygens. And so that's going to be more stable and thus more acidic. So the correct answer here is HB is going to be the more acidic proton, and that's because of resonance. Another example would be something like this. Right? HA or HB, right? So we're thinking about charge. They're both neutral, atom effects, both carbon, resonance. There's no resonance structures here. And so now we are up to hybridization. And so we can tell this carbon right here is sp2, so it's kind of 33% S, if you will, whereas this one is sp, or kind of 50% S character, if you will. And so more S character, more acidic. So the correct answer here would be HB because of hybridization. Let's take a look at another example. Right, which one of these is more acidic? Right, and so again, what you really want to think about is the stability of the conjugate base. The more stable conjugate base will be the more acidic compound. And so we can draw resonance structures for both of these if we try to deprotonate this H right here. And so at first, we can see that we have a negative charge on N. And so we're thinking, okay, same charge, same atom effect. Next thing we should go on to is resonance. And we could draw essentially the same resonance structure for both of them. And now we want to take a look at our resonance structures. Even though they both only have one resonance structure, this one's sharing a negative charge with an oxygen. This one's sharing a negative charge with a sulfur. And remember, sulfur is bigger, so S minus is more stable. And so this is going to be the weaker base, which makes this compound the stronger acid. So these problems can be quite tricky, but really that's why you want to do some practice. Let this information sink in a little bit. And of course, it wouldn't be chemistry without some exceptions. Right, so this gives you a general idea and you can compare and contrast, but there's always going to be exceptions. In reality, if possible, you should check your pKa table. But a lot of times that's not going to be possible, right? We're not really concerned about memorizing these numbers. We're concerned about understanding the reasons why. And so we'll use our rules and we'll follow our rules. There's only one exception that I really want you to know about. So the main exception that I want you to know about is that a negative charge on nitrogen is not as stable as you might think. Right? It's a relatively electronegative element. And so students often think a negative charge on a nitrogen is not that big of a deal, but it's not quite as stable as what you would think. And so maybe what you would predict here in these series of molecules, water, NH3, and sp carbon, sp2, and then sp3 carbon attached to a hydrogen, what you might predict as we're going to the left is that we become more acidic. However, in reality, we have a movement of one of these in our table. So this NH3 actually moves over here. And so the true order goes this H2O, this sp carbon, then NH3, then the sp2, and then the sp, right? And if you check a pKa table, you'll find this is true. Right here, we have our sp3 carbon, and you can see it's more acidic than this nitrogen, right? This NH3. And so the exception, again, that I want you to know is that you want to know that sp-CH bonds are more acidic than NH bonds. But then I also want you to know that it's just sp-CH bonds, right? NH bonds are still more acidic than sp2 or sp3-CH bonds, right? And you can see that in this table as well, as these two sp3 and sp2 carbons are indeed less acidic than NH3. So again, a lot of information here, a lot of ways to trick you up. You got to do some practice.